Okay, and guys, now we are live. So hello and welcome everybody to the Dotnetos Conference 2021. My name is Łukasz Pyrzyk, and today with me we have Szymon Kulec, known as Kulec, Konrad Kokosa. We are from Dotnetos, and we also have our guest Zoltán Lehóczky, who is a co-founder and managing director of the Lombic Technologies. Before we jump into the Zoltán's presentation, I just need a few minutes to briefly open the conference. So let me share the screen. So this year's conference will last 3 days. Each day we will have 3 presentations, and each session will take approximately 45 minutes with 15 minutes break in between. Each presentation is a separated YouTube video material, so you can't use the same link. However, you can use our YouTube playlist to grab our sessions into one place and watch them later on one after another. You can use this bit.ly link, or you can find the link to the playlist just under our YouTube video in the description section. Before we jump to the .NET world, it should be mentioned that this conference wouldn't have happened with help of our great sponsors. So our first platinum sponsor is company Demand. That company employs almost 4,000 high-class engineers and specialists. Everyday professional work on the development and implementation of technologies that create life-changing differences through hearing health. Our second platinum sponsor is KMD Poland, the largest foreign branch of KMD Group. They are responsible for important solutions and processes in the IT, R&D, finance, HR, and also support areas. We have also 2 gold sponsors. The first sponsor is Dotnetos Academy. It's our online platform where you can learn more about programming in .NET, correctness, and performance. You can select between various courses, including Async Expert, .NET Memory Expert, .NET Diagnostic Expert, or even C# 9 Professional. You can join for free and enroll to the Dotnetos Essential course to preview content of all courses. Our last sponsor is JetBrains. JetBrains is a cutting-edge software vendor that specializes in creation of intelligent development tools, for example, Rider or ReSharper. For sure, you used one of their products. I'm pretty sure about this. And during the conference and afterwards, you can use Dotnetos hashtag on social media. So you can find us on Twitter, Instagram, and Facebook. So please follow our profiles and use the hashtag to communicate with us. We also encourage you to visit our website to learn more about our initiative. And that's basically all from me. Thank you for this quick introduction to the conference, and I'm giving screen back to Zoltán. So Zoltán, the stage is yours.
Thank you, Łukasz. Well, hello everyone. Let me just go on and share my screen. And it's supposedly up now. Let me know, Łukasz, if something is not visible there or something
Sure,
strange.
I will be in the background just to help you.
Well, welcome everyone. I'm Zoltán Lehóczky, as you have heard. By the way, my name does seem like a bit Polish, Czech, but it's a T. Although Lehóczky sounds quite cool as well. Now, why I wanted to give you this talk here at Dotnetos, because Dotnetos is already about hardcore .NET. If you are here, then you want to see what you can do with .NET in going into the very hardcore stuff as well. And I really wanted for you to feel even more powerful, because I think I can show you something that you didn't know you can do with your existing .NET knowledge, with your existing .NET tools. And that is, well, create computer chips pretty much. Take your .NET code and turn it into a piece of logic hardware. I think it's pretty cool. So without further ado, let's go. Before going any further, just a tiny bit of introduction. As we have heard, I'm from a company called Lombic Technologies. We are based in Budapest, Hungary, but all of our clients are foreign, mostly from the English-speaking world and mostly from the US. We do web development services day to day. mostly with open source .NET CMS called Orchard Core. Probably some of you have heard of it here. Our clients are even companies like Live Nation or Microsoft, or government institutions like the Smithsonian Institution. And that's the day-to-day. But when we are not doing some Orchard development, then we are doing some research and development with Heslier. So, what is it? But actually, let's first talk about you. Now, let's suppose that you are doing some number crunching. Probably that's actually a good guess, since you are already here. By number crunching, I mean some compute bound, the CPU bound or memory bound computations. Something like artificial intelligence or machine learning, image or video processing, or even computer vision. Perhaps algorithmic trading on the stock markets, like high frequency trading, or you do anything with any kind of data compression, or something with cryptography, or perhaps cryptocurrencies. Now, once you have an application or a specific algorithm in that space, then perhaps you want to make it faster. What can you do? The usual run book. Of course, first you have to profile and optimize it, check out what's slow, and try to make it faster without doing anything even more drastic. Let's suppose that you have already done that. After that, you can, of course, parallelize it. Nowadays, every device has multiple CPU cores. It's not sure that you can actually utilize them, because all of them are up to your application to use, but you can usually also parallelize your algorithms. Let's suppose that you have done that as well. And lastly, of course, you can just use faster hardware. If it's a specific hardware, you can scale up in the cloud, and you can also use more machines, more hardware. You can scale out horizontally, which in the cloud is, again, just a flip of a switch pretty much. Let's suppose we have done that as well. Now, what else can you do? Well, the last big option, I think, is to take the heterogeneous computing approach. So when you're writing .NET code, that usually runs on a CPU of some kind of device. But there are, of course, GPUs as well. So pretty much video cards that you can also utilize to run and accelerate specific computations. And there are also something called FPGAs. Now, let's talk about FPGAs a bit more. FPGAs are field programmable gate arrays, which means that they are chips that can behave pretty much like any other computer chip, within certain limitations, of course. So, that means that these are reconfigurable chips. We could also say you can dynamically rewire them from the inside, so they can compute something else. Now, if you haven't worked with FPGAs before, I'm pretty sure that you have used them in some way already. For example, if you Google something on Bing, as Scott Hanselman says, or if you have used pretty much anything in Azure, then you have already used them. And both of these services use FPGAs behind the scenes, Bing to accelerate search results, and Azure for software-defined networking. And FPGAs are sometimes also used in household appliances like routers, or not so household appliances like X-ray machines, PET, MRI scans, or even self-driving vehicles. To utilize them, though, you need to be a hardware engineer or access hardware engineering skills, because, well, it's hardware development. You are creating a piece of logic hardware. Now, to alleviate some confusion you might have, although FPGAs sometimes have visible circuit boards and visible chips, they have nothing to do with Raspberry Pis, for example, that may look a bit similar at the first glance, because Raspberries are computers and not FPGAs. Microcontroller platforms like the Arduino have nothing to do with FPGAs either, although I've seen some projects where they couple FPGAs with Arduinos or perhaps even with a Raspberry. Now, why would you care about FPGAs to begin with? Why is it interesting? Well, to answer that, let me show you some very crude, very unscientific comparison between different computing devices, just to give you an idea. So let's talk about what CPUs can do, so something that we have in every device of ours, and what GPUs can do, which are included in pretty much every personal computing devices as well, even if you are not working with them as a software developer, and FPGAs that look a bit exotic here. Let's talk about parallelism, so how much stuff you can compute at the same time on these devices. And now the first chart. Now I think that CPUs are pretty much on the lower end here, the bar in blue, because on a CPU you have perhaps 32, 64 cores if you are going to the high-end ones, but that's about it. That's how many computations can do at the same time. With GPUs, they are on the upper end here, because GPUs can have thousands of little processing cores that can all compute things in parallel. And FPGAs in gray I think, are kind of in between, because you don't really have cores on an FPGA, although that's not entirely true nowadays. But the level of parallelism you can get on an FPGA is roughly in the order of hundreds, sometimes thousands. Now, of course, all of this depends greatly on the specific device you are using and also on your use cases. All right, the parallelism is out of the way. What about the complexity of programs you can run on these devices? CPUs, I think, win here, because if it's a program, you can run it on a CPU. GPUs are on the other end, but on the lower here, because the programming model on a GPU is much more limited. While with FPGAs, I think it's kind of in between again. Although you are not really writing a program for an FPGA, but rather you are implementing your program as a piece of hardware there. But still, I think what you can do there is somewhere in between. And lastly, power efficiency. How much stuff you can compute with 1 watt of power? I think that CPUs and GPUs are roughly on the same level here. Again, simplifying, but FPGAs really shine. FPGAs are very power efficient devices. And the reason for that is because an FPGA just computes what you need to be computed. There is no operating system and no other programs to run. There is not even an instruction set like for any processor, but it just computes what you need it to do. The logic is hardwired there. Okay, so that's great. But there is a huge downside, and that is that it's very hard to use, very hard to work with FPGAs as a developer. Because, pretty much everybody can program a CPU somehow. GPU programming is fairly accessible nowadays as well, but FPGAs are something completely different. You are not writing a software for a processor, but you are creating a piece of logic hardware. You have to think in terms of wires and logic gates and clock cycles. It's super low level. But with tools like Heslier, we intend to bring this down to the software development level. Okay, so all of this sounds cool, but what is Heslier then? Heslier, you could say, is a tool that takes a computer program and creates some equivalent FPGA logic out of it. Or we could also say that it takes a computer program and creates a computer chip out of it. Although we are not going to a foundry to actually get that chip manufactured, we are rewiring an FPGA. We could also say that we take some logic, which was formerly expressed as software, and create some equivalent logic, which is now expressed in a hardware form. And of course, we are at the .NET Conference, not just any software, but .NET. Theoretically, that's any .NET language. We have C# examples, we have an F# example, but we could even have PHP examples with PHP. So all in all, what we aim for is to get the benefits of FPGA computing for all of us software developers. That means that you can get a substantial performance increase if your computation is highly parallelizable and is CPU bound or memory bound or both. And at the same time, you can get a higher power efficiency. So you can compute more stuff with less amount of power. Now, that latter part is also quite important if you are thinking in terms of data centers, because data centers use huge amounts of power. You can get quite a bit of power saving there if you move computations to FPGAs, which is, well, good for the environment and also good cost-wise. And all of this is still software development as usual. All right, a lot of talk. Let's see it in action, actually. So I will now switch to Visual Studio and show you some code. And actually, it won't just be any code. I thought that I will show you how this works in the cloud, because it can work in any major cloud, including Azure and AWS. But I would like to show you space-ready software. I would like to show you how you can use the same knowledge that you already have in .NET, and with Heslier, write softwares for spaceships, for satellites. And that's just a little bit of a stretch. I'm not lying there. Let me go there. So Visual Studio, as we all know, and what I'm showing you here is well, a class which, as the name suggests, implements a highly parallelized algorithm. This is one of the examples that we have for Heslier. It's part of the SDK up on GitHub, so you can check them out in detail too. But this is just a very simple, very synthetic example. This is not some real stuff, but it kind of shows what kind of algorithms are especially suited to be accelerated with Heslier and with FPGAs. And what this parallel algorithm does is something quite simple. It takes an input number, and then it starts some tasks here, task parallel library tasks. And it starts this many tasks, which is 280. Now, why 280? Because this many will fit on our FPGA. What we are looking at here is standard .NET, standard C#, but Heslier will process the whole thing and turn it into a hardware implementation. When we start tasks here, those will run when executed on a standard PC. For example, they will run as threads on a CPU. But if you convert this into a piece of hardware, then we'll get this many little, well, processing cores. 280 in this case. Now, the .NET thread pool will take care of not oversaturating the CPU if there are fewer than 280 cores, which is most possibly the case. But on the hardware, we will get pretty much a 280 core processor for just our application. And what happens in these tasks is here there is a bit of conditional logic which is executed 10 million times, and then the result is returned back. Finally, we wait for all of these tasks to finish, and once they are done, we sum together their outputs, and that will be the output of the whole algorithm. So as you can see, it's a mock algorithm which is massively parallelizable, or embarrassingly parallel, as they also say. And I have an FPGA here. This is what I will use for this demo. This is the device that I will execute this application on. This is an development board. The actual FPGA is the little thing here in the middle. The whole big board with the Ethernet ports and everything is just the development motherboard. And it runs Linux. a Linux distribution called PetaLinux, and now I'm connecting to it via serial shell. Why this hardware is very special is because this is pretty much the same hardware that's available as the onboard computer of embedded devices like drones or robots or satellites. I'm not kidding you. Pretty much this little CPU with an FPGA is the onboard computer of many new space small satellites. Because while it can run why it can run a Linux, because this is not just an FPGA. This is an ARM CPU coupled together with an FPGA. It's a dual-core ARM CPU, pretty much something that like you have in your smartphone. And now I will run the demo here. What happens is that first Heslier generates the hardware implementation. This is not something that you do once your code is in orbit, but I'm just showing you here to show that it was, well, quite fast because it's already done. Then what happens is that first we execute the parallel algorithm sample as simple software, so on this dual-core ARM CPU. And as you can see, it happens. It was about 25 seconds. And then we executed the same thing on the hardware 3 times. So let's look at the results. Let me scroll back so we can inspect what happened here. Well, first of all, the CPU execution took about 25 seconds, so quite a lot. Now let's see what happened on the FPGA. If we scroll down, we will see the numbers corresponding to that as well. We have some nice ASCII art here too. and the result is here. If you take a look at it here, it was about 240 milliseconds on the FPGA. If we take the FPGA execution, just what happens on the happened on the hardware into account. If you also count the communication round trip between the FPGA and the CPU, then it was about 300 milliseconds. Sorry, I have a bit of a cold, unfortunately. Just at the right time for Dotnetos, of course. So, so our FPGA implementation was about 100 times faster. That's a lot. That's something worth pursuing. Now, if you take a closer look, by the way, it wasn't just a lot faster, but the FPGA implementation is also reliably faster, because first it was 240 milliseconds, and then the second execution was pretty much exactly the same, and the third one as well. Now, how long it took to get from the FPGA to the CPU varies, because the CPU is still a device that runs other software and Linux itself. But the hardware execution is deterministic. That's one of the other advantages of FPGA execution, because, again, there's nothing else to run. It just focuses what you need to be computed. There's nothing else, no operating system, no other software. It takes exactly the same amount of time every time. Of course, this is quite useful in in scenarios where you need ultimate reliability, like well, on board of a spacecraft. Now, let me get back to Visual Studio for a minute, because here we had our parallel algorithm sample, but where does the whole thing actually start? How do we communicate with Heslier? How do we tell Heslier to make this into a hardware? What's behind the scenes? Well, all of this is just part of and again, a super simple console application that we have here. And basically what you have to do for Heslier is to use Heslier from your software is create what we call a Heslier shell, pretty much, and then do some configuration first. You need to configure what kind of device you are using. This ugly technical name is for the sample device here. And then you pretty much tell Heslier that, hey, I want my parallel algorithm to be accessible as a hardware implementation. Then there's a bit more configuration that's less interesting. And finally, you generate the hardware with Heslier. This is where you pass the assembly that this algorithm is part of to Heslier, and Heslier will create the hardware implementation. And once that's done, you start the actual hardware execution. First we had a CPU execution here, but after that, here's the hardware execution. Now, you may notice that there's not much to notice, actually. It just looks and behaves like a standard C#. And the reason for that is because that's what's happening. There's one trick, this generate proxy call here. This is where you take the instance of your parallel algorithm, of your software implementation, and Heslier will wrap it into a dynamic proxy. So subsequently, it can redirect calls onto the hardware implementation. So after that, you just call methods on your parallel algorithm as usual, but in reality, the call is transferred to the FPGA implementation. It's as seamless as possible. You can pretty much use the FPGA as your application-specific coprocessor. You offload computations onto that, which is pretty much what happens with any hardware accelerator, GPUs included. And one more thing here. You may wonder that, okay, we have this magical generate hardware call here. What's actually happening there? What's the magic? And of course, it's always good to see one step behind the abstraction that you are working on, the level of abstraction you are working on. So what's happening there? Well, what's happening there is that Heslier creates some code. It creates some code that normally a hardware engineer would write. And this code looks like this. What we are looking at is, well, not .NET. And while it's code, it's not software either. This is hardware code. This is written in a language called VHDL, which is a hardware description language. So while it has, for example, ifs and if-else here, you may would guess that, well, this is a program, right? Well, it isn't. Although there is an if, in the end, this whole thing will be a piece of logic hardware. You could actually generate a computer chip out of it, a physical one, get it manufactured, but well, rewiring an FPGA is a bit easier, of course. And well, there's a lot of stuff here. This is something that you can, by the way, also check out if you are interested in hardware development. But what I wanted to show you here is a bit down. Specifically, we can notice the name parallel algorithm here. So this is familiar. We are seeing a pattern here, and if we scroll down, we may see a pattern here as well. So there's this first thing, and then there is the same thing again, but the first thing is with the index 0, and the second thing related to parallel algorithm is with the index 1, and then 2, and then 3. Well, this is curious, right? So we seem to have copies of something related to parallel algorithm. And indeed, what we have here are, this is not the whole algorithm implementation. These are just the type declarations yet. The whole code is a bit dumb. It's very long. But we have copies pretty much of parallel algorithm here. And if we scroll down a lot more, we may see that we have the same thing again with the index 260. And if we scroll down a bit more with 271, and even more, we'll find the last one with 279. Remember that we started 280 tasks? Here we have the copies. Here we have the actual hardware level parallelism. Here we have all the little processing cores laid out for our parallel algorithm implementation. Pretty much all the code that we had here within the task is repeated 280 times. We get some hardware level parallelism for our algorithm. We are not limited by the 4, 8, 64 cores of a CPU, but we get a processor that has that many cores, that level of parallelization that we actually need. Now, of course, FPGAs are not infinite. So at one point, it will be just full. As mentioned, for this specific device that I have here, that we can put on board of satellites, the limit is about 280. For bigger cloud FPGAs, this can be 10 times bigger. And of course, for smaller ones, you will get tighter limitations. So I hope this was cool. Let me also show you a bit how the actual device that I have here looks, because probably in the webcam the picture wasn't that perfect. This is what I've shown you, and this actually looks quite big on this picture, and if you are full screen, then probably it's very big. But the device itself is actually just like pretty much 2 thumbs, just that big. It's very small, and the FPGA itself, with the ARM CPU together, is this little chip in the middle. It's smaller than a fingertip, and this is pretty much the core of the whole thing. This is the brains of onboard computers for satellites and drones, as I mentioned. And why the whole thing is a bit bigger that I had in my hand is because we have this carrier board here, and we plug the FPGA board into that in the middle. Also, it has some ports. We can have a proper power supply and everything. All right. Well, that's about it. Well, not really. We also have support for cloud FPGAs, as I mentioned, which is with a development environment called Vitis. We are foremost targeting the devices of the biggest FPGA manufacturer called Xilinx, and those cloud FPGAs, what they call data center accelerator cards, are available in pretty much every major cloud. In Azure, they have been generally available for maybe half a year or so. In Amazon Web Services for a bit longer, and there are other cloud providers too. Now, I said that I wanted to show you something very cool with the space-ready hardware, but probably a more day-to-day, more practically applicable thing for you is indeed the cloud. And in the cloud, we have these Xilinx Alveo cards where we see quite good results as well. Well, unfortunately, not quite as spectacular as this 100 times faster one with the parallel algorithm I've shown you. But we still see, for example, about a 30-time speed increase for image processing tasks. Now, image processing is also typically something that you would use FPGAs for, and also something that you can utilize in a lot of applications, even in a web application. If you have an image gallery where people upload hundreds of or thousands of images every minute. And at the same time, again, you get a power advantage, power efficiency advantage. So it's about 30 times faster, but it's almost 120 times less energy consuming, which again is good for the environment and also good for your pocket. One more cool thing that you can that you can do with Heslier as a .NET developer is create your own number format. Now, we have floats and doubles in .NET that we use every day in some way when we want to store fractions of numbers. But those are not the only way to do that. Actually, the standards those number formats are built on are quite old nowadays. I think they are from the 70s. And there have been numerous research going on to make better floating point numbers. Better floating point for some specific use cases. Nowadays, is mostly for machine learning. And one of these number formats is called POSIX. This is developed by Dr. John Gustafsson, a researcher currently working in Singapore. And POSIX promise to have better range and better accuracy than the floats that we use today. So it promises to make our computers provide better answers to numerical questions. Now, this is quite important for engineering tasks or scientific computations. And what we have done is that we have created a .NET library that implements such a number format. So pretty much we have a POSIX struct. And the cool thing there is that why you can use that as .NET code, as a piece of .NET software in your .NET program, since we have created it in a way that is compatible with Heslier, we can also create pretty much a POSIX processor out of it. So, you have a custom number format, but within pretty much a few minutes, you can get a processor that accelerates computations with your custom number format. How cool is that? And we have a few more things lined up. We want to have more examples, more real-life use cases, or we have quite a few already, but we want to see more where this technology can be applied. Our partnership with the Wiener Research Center for Physics is also for that. Of course, they are big in scientific computations. And as I mentioned, FPGAs are nowadays in every major data center. AWS, Azure already has them. And not just that, but we had some pretty big mergers nowadays. Intel, the biggest CPU manufacturer, bought the second biggest FPGA manufacturer called Altera a couple of years ago. So now Intel is an FPGA manufacturer. And AMD wasn't falling behind, and they bought the biggest FPGA manufacturer, Xilinx. So I think that we'll see a lot more synergies between CPU computing and FPGA computing. Intel already did a couple of researches on that front by putting FPGAs into their CPUs. As I've shown, although not with an AMD CPU, but with an ARM CPU, Xilinx has done the same thing. I guess that pretty soon we'll see more from AMD on that front too. And although FPGAs are not really in every computer yet, we can't really keep up Moore's law much longer because we have physical limits, unfortunately. But still, we want our computations to be faster, more efficient, more energy efficient, especially nowadays. And FPGAs offer a very good tool for that. So pretty much that was it. If you like this, and I really hope you did, then check out the whole thing on GitHub. What I've shown you, the SDK is up there. And be ready because FPGAs are coming. Now, can you remember GPUs and how it started, the general purpose GPU computing? Probably it was 10 years ago. It was quite a niche. Some people, I think first from academia, perhaps from physics, wanted to use GPUs for their computations. But GPUs were just used to create video signals at the time. So they hacked around. The people from the Wiener Research Center for Physics did that as well. And they somehow made it working. And since then, the whole thing got adopted by the GPU manufacturers. Now they are manufacturing GPUs specifically for general purpose computing. So not video cards anymore, but accelerator cards. And we have nice, convenient SDKs, wide array of language support for GPU computing. And I think the same thing is happening with FPGAs, because FPGAs are, again, another very useful computing device with their unique advantages compared to CPUs or GPUs. But it's a bit of a niche still. It's not easy to use them if you're a software developer. Heck, it's not even easy to use them if you're a hardware developer. But this is changing. We are seeing some very large improvements there, both from Intel and from Xilinx/AMD. So I think we'll see a lot more FPGA computations in the future. So thank you. Feel free to get in touch with me if you have any further questions, or if you have a cool use case for Heslier. I would be happy to hear from this. Otherwise, check out the website, or again, the SDK on GitHub. Or if you are interested in the company behind Heslier, well, lomig.com has all the answers. And I believe we have some time for questions as well, if there are any.
Yes, we have 3 minutes, so we can take some questions. I see that we don't have any questions, let's say, from the live perspective. So if you have any further questions, you can always leave them as a comment, and we will try to get Zoltán in touch with you or answer the questions by ourselves. Okay, we have the first question about troubleshooting.
All right, great.
So Ahmed asks a question about troubleshooting. So can you explain us how to attach, for example, a debugger, or what are the possibilities to enter the hardware and see what's going on if you want to investigate the problem?
Mm-hmm. Yeah, great question, and that's a hard part. Well, first of all, you should debug in software. So they shouldn't really be any differences in the hardware execution and the software execution. If there is, then that's not a bug in your software, but that's a bug in Heslier, which of course is not really perfect, so it can happen. Unfortunately, if there's anything going wrong just on the hardware, then, well, you have to use hardware engineering tools, like pretty much tapping into the signals traveling on the chip. This is something that we do while developing Heslier. So you can look into it if you are specifically interested for some reason. Otherwise, it's a bit better to just open an issue on GitHub.
Thank you for the answer. Okie dokie, then I think it's all. If you have any further questions, just leave a comment in the YouTube and I will try to get an answer for you. And from my side and Dotnetos, thank you, Zoltán, very much for the presentation and your presence at the Dotnetos conference. It was great for me to see FPGA, Linux, and .NET in action at the same time. I bet 10 years ago, no .NET developer would expect that, and now we can see how it works. And for the audience, yeah, feel free to grab a link to the playlist and see you on the next presentation.
Yes, that's thanks to the cross-platform nature of that started with .NET Core. So thank you. I will stick around for the whole conference. Bye, everyone.
Yeah, thank you. Bye bye.